So here, let me replay the whole calculations. Okay, so here we have the same governing equations, and what I want to try. So m equal to 1, c equal to 2, k equal to 1. By doing so, we can achieve the quickly damped systems. So let me modify the whole thing. If you like, you can rewrite, repeating the whole the writings, or you simply can take a look at it and later on someone take the pictures. Okay, so take a picture of the board. So here, let me modify the things quickly. Okay, so right now we have the x of s equal to this one. And again, right now we're still taking the unit step input for the illustrations. And so the unit step input Laplace transform is this. So by the block diagrams, the output equal to the gain multiplied with input, just like this. And then this is x of s. So we're going to calculate the f of t, so we take the inverse, okay? So this one will be s plus 1 squared, and with this one. So how to do this one here? We can look at the table. I don't know why. Do it out. So let me look for I will find one and write on the board. This one. I found on the lecture notes if this is the time function, the Laplace function, and then here we might be able to use is this one. Okay, I found that one. We might be able to use this one. And then how can we use? I think the first step is this one. To this step, I think it's a little bit too early. So for this one, I need to decompose this first and say decompose into as a plus s squared plus 2s plus 1. Bs plus c. Okay. So to find out those things, then I simply basically this one, let me rewrite as squared plus 2s plus 1 and do the calculation. That is a s squared plus 2s plus 1 plus b s plus c times s. So I compare this one, compare the coefficient as s squared plus 2s plus 1, this one. So compare the coefficients of the numerator polynomial. So from here we compare, then we can say the square term is a plus, this is s, b equal to 0, and as one term, that is 2a plus cs plus c equal to 0, and then the s0 term is only a equal to 1. Will I be right? Okay, so from here we can obtain the a equal to 1, and b equal to minus 1, and c equal to minus 2a minus 2. So from here we have the information is a equal to 1 here, and b equal to minus 1, c equal to 2 minus 2. Okay, so here we can do the Laplace transform, and I need to erase this. Then here we can this term, let me do a little bit arrangement. This one basically equal to s plus 1 squared, s plus 1 plus s plus 1 squared 1, right? I simply split the numerator into the two terms. So in this way, this will be equal to s plus 1 plus s plus 1 squared. So therefore here the inverse is basically conducting onto here, s plus 1 minus inverse and s plus 1 squared. Am I okay? Okay, so on this one, then here we have let me write down if this is 1 over s, then this is 1. So we utilize this one here. So here this will be basically equal to 1. And then for this one, s plus 8, this one basically is minus 80. So for this one, the second one is minus 80, minus t.
Is there?
Is that right?
It's not.
Hmm? This one equal to s plus 1 squared, s plus 1 plus 1, right? So that equal to this one. Any mistake? Seems okay, right? I didn't prepare for this one. Any doubt? Said. It's okay, right? Okay, now we continue. So for this one, right now, for the last term, we apply, it's applied to this one here. If you look at this carefully, then n equal to 1 for our last term, n equal to 1 for our last term, and then a equal to 1 here. So that means becoming into e minus t and t. Yes. Where? Here?
Yeah, that's not right.
This is not right.
That's not right.
So where's the mistake?
Because when you do the partial the partial fraction decomposition of that, it should be, so you have a over s plus b over s plus 1 plus c over s plus 1 quantity squared. No.
Okay, for this
because
one,
you only bring out the bs plus c, like you only have that type of term when you have an s, like something that doesn't factor.
If you don't factor it, you still use BS plus B. You don't have to factor.
For this one, let me do this one again. So our question is s plus 1 squared, right? We're going to factorize. So basically here is this s over a plus s plus 1.
Something like
If
that.
you
And then taking the inverse plus of that.
It's nicer, yes, but it's not necessary.
like this.
Oh wait, fine, never mind.
Never mind.
Never mind. Forget it. Forget it.
So this one basically is equal to
Just the thermometer.
1 minus e minus t, 1 plus t. So that, assuming this process is correct, cover this, I provide you a bonus. If anyone can find out a mistake, I give you
You're
1
fine.
point.
No, it's fine.
I give you 1 point.
It's fine.
Okay. I'm not sure, so
No,
I
it's
need
fine.
your,
You're supposed to write that.
So I'm
Okay.
gonna throw my
assuming this
pencil
right,
at you.
then we can continue. So right now we can see, we can draw the time domain response. This is t, and this is x of t. And the value is 1 superposed to these components here, and that one is minus. you can use the MATLAB. Eventually this term will be decaying to 0, right? This term when t approaching to infinity is going to be 0. Okay, so eventually the whole system will be, I don't know the process, but eventually I will go to here, converging to the value of 1. Then we back to here for the complex domain. So let me rearrange, let me get everything back here. So basically here for our example, then that should be equal to at 1, 1 here. 1, 1, so that is here. And what is time now?
11:25.
25, okay, still have 5 minutes. So this is the location of the poles. So again, the natural frequency simply is this. The distance you measure omega n equal to square 2. And this angle, this is cosine zeta. So therefore zeta equal to cosine equal to 45 degrees. So zeta equal to 1 square 2. And compared to our characteristic equations, using the standard, this is 2 zeta omega n, and omega n squared here basically equal to 1. Okay, the coefficient here equal to 1. So from here, either you compare with the standard expression, you can reach the same result here. Okay, so, and for the third one is the overdamped systems. For the crudely damped system, they shouldn't have any oscillation. You can verify. You can verify. And for the third one is overdamped system. And for this one, I will leave you for your exercise, but let me give one example here. For the third one, for example, let me say this is 3. This is 2. Okay, and give a try. And the results should be very straightforward, and give a try. This one even, for the analysis of the two critically or overdamped system, that is temperature ratio is greater than 1. Oh, my mistake here.
Yeah, because that can't be 1 over square root. That zeta can't be 1 over square root 2, can
My
it?
mistake here.
Because you're not going to have imaginary numbers.
Yes. The value here is -1. We have repeated poles at -1, and damping ratio should be equal to 1.
1, yeah.
Okay. And for the third one, you should be able to find this for the overdamped system. For the third one, for the overdamped system, for your own exercise, the locations, the real part, the imaginary part, and that's located at here, -1 and -2, for your reference. Okay. So I think we fall behind the lectures by about 1 hour, and then hopefully Friday I can quickly finish the modeling. But this one basically lay down all the native calculation for the modeling. And again, later on for the modeling, I will go very quick. Again, because as long as you can map all these numbers into the standard differential equation, you simply repeat the calculation.